Do you have a hard cutoff at noon?
I'm Maria. I'm more than happy. The rest of the day is actually free. It's free.
Okay.
It's pretty much free, so I can spill over and actually, again, it was provocative. The title is provocative to have conversations here.
Okay, great. Okay, welcome. Yeah.
So I don't know if I can share my screen.
Yes.
I do have some slides.
We can see it. Yeah. Okay.
Good. Excellent. So I'll start off the bat by thanking two of my new graduate students working with me. We've had this presentation is somewhat the result of ongoing conversations I'm having with two great new grad students, Abdelrahman Ayad and Jialun Zhang, who I really want to acknowledge their contribution to the thought-provoking thoughts I'm gonna share with you today. So I'm with the Department of Electrical and Computer Engineering at McGill. I've been there for now 10 years, more than 10 years, 11 years actually. And before that, I was at the University of Manchester. Okay, so I'll start. And again, please feel free to stop me if you have any questions as we go along, or if you disagree strongly with what I'm going to say. So I guess if I can get this to move, yes. So when I'm talking about networks, at the end of the day, why electricity networks? And it goes back to at one time I've been, and I'm again, Maria, we've been a speaker on these speaker series where I'm organizing summer schools for undergraduate students to get them interested in what we do for research and what the industry is interested at least in knowing. And I once had a presentation from Tim Green from Imperial College London, and Tim went off the bat, started up saying, why do we have electricity grids? Why don't we have each of us have a little Honda generator in our backyard to power our home? And really made me think. And clearly, obviously, if you go back to Edison, well, Edison could not put a power plant in every single building. You still had to, you had Pearl Street Station, and then you had a little bit of transmission a few blocks down the road to send DC power to the different buildings. But at the end of the day, the beauty of electrical networks is, and again, we talk about the sharing economy, Uber, Lyft, whatnot. And really at the end of the day, electricity grids are the primary element of sharing that we can think about. So we don't all boil water at the same time. We don't all do things. Yes, there's some people who are, we all get up in the morning, we all go back home, we all go to bed. As I tell my undergrad students, humans are very predictable. We go through the infinite loop of life. But at the end of the day, we don't all do the same thing relatively at the same time. So there's great value in having all of us pooling our resources together, be it not just in terms of generation, but also in terms of use. So there's clearly economies of scale there. And also, again, we're talking about, especially, I'm going to use a lot of examples from where I'm from, Quebec. And we're looking at, the problem is that Hydro-Quebec has been, signing contracts left, right, and center with utilities or states. So for example, Massachusetts, with the city of New York, or the state of New York for sending electricity in places where, again, it's primarily carbon based electricity generation to try to displace some of it. So economic opportunities really come out also from having grids. And at the end, the other thing I really get often, we don't get that much here in Canada, or at least in Quebec, because electricity is so cheap. But I always get, I'm sure you folks in the US especially get these, the typical libertarian Arizonian with solar panels on their roof. They have a nice Tesla Powerwall in their garage, and they say, I'm just going to cut the cord and be done with it. And really, when I hear this, I get quite upset, perhaps because I'm biased. I'm an engineer, and I'm a network engineer on top of it. But at the end of the day, if we were individually all cutting the cord, I think probably the planet would not really fair, good price. Because yes, we might just use solar power to meet our needs, so that would be carbon free. But on top of that, we'd have to basically fight for the scarce resources to build these solar panels for every rooftop, build the batteries for every household or every building. So clearly, on aggregate, we'd actually have way more overcapacity than we actually have currently. And by the same token, again, that might be this is my more again, this is very much a Canadian slant on things. Only those with deep enough pockets could afford to do that. Again, there's clearly a capital. If you have free capital, then you can do it. Otherwise, you have to suffer. And as I said, also, again, it might not be the most environmentally friendly option. So the networks do, we can argue all that we can about whether or not they're ugly or they're beautiful. I tend to say they're beautiful, but again, I'm biased. So that's the other thing, or we could bury them underground if that's possible. So when I'm looking at this, what has the past told us? And here really I'm talking about sort of TND, transmission distribution. And if at least I would say in the case of the United States, and I'll take North America in general minus my own province, Quebec, typically, we're looking at, large power plants located in state or out of state, but within, roughly 250, 200 kilometers radius from where that electricity was basically expected to be produced. So, and also this is sort of compounded by the fact that, unlike, for example, if you look at the United States, where oil and gas transmission is regulated at the federal level, electricity grids at the beginning, at least, were developed, on a statewide, on a state basis, on a state-by-state basis. And in Canada also is the same thing, where electricity generation, transmission, distribution, and retail is under jurisdiction of the different provinces. So that's why typically you see a lot of north-south flows between, for example, Canadian provinces and the United States, but there's very, very little interconnection on the east-west corridor, which is sometimes people ask us, this is completely crazy. You should be selling across the borders, but it's not working. And really, this is an institutional artifact that created this situation. Obviously, everything has been built for the peak with some margins. Transmission has been meshed, in our case, at least in the case of Quebec, very much overbuilt, or if not, I would say even gold-plated. And it really relies on a lot of automatic control actions for reliability purposes. And again, Maria probably knows way more than I do about this, all these special protection schemes, different approaches to make sure that very bad disturbances don't propagate and don't knock everything down. So there's a lot of investment in keeping our transmission system up and running 24/7. On the other end, distribution's been, it's very, it's radial, it's passive. Why? Because it's pervasive, it's everywhere. Typically, I think I'd say in the United States, you have a 3-to-1 ratio of miles of distribution versus miles of transmission. So clearly, it's much more exposed to the elements. It's much more exposed to drunk drivers. It's much more exposed to all sorts of dangers that could actually bring it down. So so for example, in the case of, I put a little caveat at the bottom of the slide there. So in the case of Quebec and Manitoba, Canadian provinces, which decided in the 1970s to go and develop large-scale hydro in the north, this is where the transmission is quite different in comparison to other places in the US and Canada. So that's kind of the exception here. So what, oops, sorry, what's going on here? Sorry about that, folks. Okay, so I guess then the next question is what would drive us to actually try to go with radical network design changes? Well, for me, the first thing that at least comes to mind is the fact that generation has completely changed its nature. And So now we're seeing large-scale wind, large-scale solar developments, be it offshore for wind or even inland, for example, in the plains in Iowa and sort of in the MISO territory in the US. So clearly the wind is where it's windy, and where you've got PV where it's sunny. So essentially what, for example, Quebec and Manitoba have gone through, well, there is going to happen also in the US. And, for those of you who might have not seen it, I think John Oliver from on HBO, what is the name of the show? Last Week Tonight with John Oliver did a quite nice piece to really tell the US citizens that this is going to happen if we want to decarbonize. And there's a lot of wind in the middle, but there's a lot of load on the coasts. So transmission will be essential to make that happen. And so really when we're looking at what the transformation that's going to have to happen, at least in the US and Canada on a more global scale, Quebec and Manitoba have kind of seen that already. And it's kind of already part of how we work with our network. By the same token, also in that same area, distributed energy resources are really making a radical change in how generation is coming in. So generation is no longer in a few discrete locations, it's everywhere. So PV on the roof, rooftop PV, energy storage behind the meter also, all these little resources together should not be just left there to just do whatever they want, but effectively, I think they should be considered a network resource, and they should be sort of at least in some way coordinated to give something bigger than the sum of their own capacities. So really this is, to make that happen, we're going to need to think more radically, more differently. Natural disasters also have sort of rang the bell here. So I'll give you some examples from Quebec. So in 1989, there was a major geomagnetic storm, which basically led to a province-wide blackout. And this, again, was really caused by the fact that we've got north-south lines that are quite long, about over 1,000 kilometers long. And because of the north-south direction, the way the magnetic field, so basically magnetic fields created by the solar wind creates DC currents, and they were basically DC currents that rushed into the neutrals of transformers, saturated cores, and everything started to come down from there. So obviously this was a major event. The ice storm of 1998, for those of you who might know, also was a major event. I was in the dark for many days. The house I'm living in, the owner at the time actually made his shed generator ready. So I actually have, between my shed, which is about 40 feet away from my house, there's an underground cable that connects to my electrical box where I could go directly connect a little Honda generator. So that, this actually changed the behavior of homeowners after these types of radical or very catastrophic events. But when you're looking at what happened in the aftermath of these two major disturbances, the response was very much an engineered response. It was, let's keep doing things the way we've been doing. So in the case of the geomagnetic storm, let's put series compensation. Series compensation will block the DC currents. We'll be, good to go. And on top of it, it helped with transient stability, and it helped with increasing the transit limits on the lines. That was like a win-win-win solution, but extremely expensive. In the case of the high storm, while they've basically they've increased the meshing around the Greater Montreal area, but that's basically it. They've not gone beyond that. Yes, they've changed some of the sub-transmission. They've added anti-cascading towers to make sure that, once a tower goes down, you don't get a domino effect. But beyond that, they've not really done anything else than that. So if you look at the distribution system, nothing has happened. It's business as usual. The only place where you've seen any sort of change, and I was interviewed I think when it was the 20th anniversary of the storm, And the journalist was flabbergasted that we've not buried more distribution lines. But it comes down that unless you are building a brand new development, digging the street and putting the lines underground is extremely expensive and it's extremely disruptive. And as a result of that, there's been very little burying of distribution lines. And typically it's only more affluent communities will afford it. So if I look at the US more specifically, I'm looking at two hurricanes. Obviously hurricanes are kind of the staple that comes year after year to disrupt either a grid. Again, I should have added the hurricane that caused problems in Louisiana this year. That was Texas with a polar vortex. But if you look at, and perhaps we're a bit, these events are too close to us to really see how they might have a lasting impact on how the grids are working. But if I'm looking at the case of Sandy, which really affected the New York, New Jersey area, one of the best example I think is how Princeton built its own microgrid. It's not just to sell ancillary services to into PJM. They want to basically tell the parents of the students, well, your kids are safe with us in Princeton. Well, you might not have electricity at home, but your kids are safe with us because we have our own microgrid to sort of be an extremely resilient campus. Then obviously Hurricane Maria was, I think, really one of those, and I know Marie, you've talked about this in the past, it represented an amazing opportunity to kind of say, let's think radically, because the whole network was down, and let's look outside the box and try to maybe do something differently. But at the end of the day, people need power to live, to be productive. So at the end of the day, let's rebuild exactly as it was before. Perhaps we'll have a bit more of openness to look at different things, but still, like it or not, we'll still be stuck with the legacy grid there. But it might, at least I don't know what are the, I've not looked at very closely into what is going on currently in Puerto Rico, but it could be one of those laboratories or living labs where different approaches could be developed. And clearly here, this is where, and I think residents of Puerto Rico have taken things in their own hands, buying solar panels, inverters, battery packs to try to harden themselves against possible future disasters. And electrification, I think, is the next big one here. Rural electrification after the Great Depression, after World War II, really made what modern farming is, at least in the US and Canada, made the lives of the farmers a lot more easier and made them a lot more productive. But this came at an enormous price. Again, very ambitious and audacious infrastructure programs to, again, electrify countrysides, and again, that came also with a lot of development in the nuclear industry. So if you look, for example, now in major parts of the United States, the United States and Canada, where we're trying to electrify transport, we're trying to electrify heating, we're trying to electrify a lot of industrial processes. So for example, in the case of Quebec, when they developed the large hydro projects up north, one of the things they've done is basically they've electrified heating across the province. Have they done it well? Absolutely not. They went with the worst case scenario, the worst technology possible, which is baseboard heating. But that did the job at the time. They needed some load because they needed some load in the south of the province. So let's just connect resistors at the end of the line to sort of make sure we use our generation. We could do it more smart. They could have done it smartly with more heat pumps instead. And I'm hoping this is what's going to happen in the US, because obviously you've got air conditioning needs on top of that. But that choice, that electrification choice, basically put a very high capital requirement on distribution feeders. So if I'm talking to my colleagues who are distribution planners at Hydro-Quebec, every single feeder is rated, and the transformer is rated for a 2 to 2.2 per unit cold load pickup amount. So effectively, you've got, for most of the time, you've got unused capacity that's just sitting there. So when we talk to electrical, distribution engineers, typically at Hydro-Quebec, do they care about people getting an EV charger at home? Not really, because overall, in terms of the capacity requirement associated with them, it's effectively the same thing as adding a hot water heater to the household. And unlike the hot water heater, which runs the whole day, this will run at a certain amount of certain times. And again, if you can program it, it's almost like it's not there. But if I look back, my time in Manchester in the UK, where you had side by side underground, you had the electricity cables and you had the gas line. Well, if all of a sudden the gas line's been kicked out, well, the electricity line and the infrastructure that goes with it will have to also be quite beefed up if you're electrifying the heating, and you need to install a lot of chargers in parking lots. So clearly there's going to be some digging going on in many, especially European cities, in the near future. And last but not least, I don't want to forget this, is that developing communities and nations also have that opportunity. And again, I think the best analogy here is how they went from no telephone to cellular phones right away. They skipped the wired portion in the middle. So really, I think there's that opportunity where there's a lot of research on community microgrids. This is, the pages and pages and pages of journals are, myself included, polluted with research in that area. But really where the next frontier is how we could technically start to interconnect these microgrids together to really create the community of communities with, again, the leveraging effects that could happen, and again, get things that are better than the initial small networks. So let's get to the crux of it, the crux of it. So why do we want to start from scratch? And when I say start from scratch, I'm not a radical revolutionary once, from a disciple of Leon Trotsky. I want just to understand on paper, if we were to start from scratch today, what would be the solution? And obviously here, and I'm going to discuss that later, the assumptions I'm going to make are obviously going to be tainting, and my own personal biases are going to be tainting the results we're going to get. And obviously this is something we need to take into account. But the first motivation is, as I've been sort of talking for the last almost 20 minutes, was that the assumptions have changed extremely radically. We're no longer building coal plants to feed a city and its industrial load and its suburban areas. Things have changed a lot. We're looking at going into tapping into wind farms that are miles and miles away. We're looking at interconnecting things that didn't even exist 2 decades ago. So the other thing also really that I think that's more my motivation as a researcher. What if there's something, as on the slides, in our blind spot that we've not seen? We might be so much in our tunnel vision that this is the way we've been doing things. And again, and going back to a number of examples we can tell, and I always get questions from students in undergrad classes. Why 3-phase? Why not 4? Why not 2? Why 3-phase is one of them? Why 60 hertz? Why 50 hertz? So, and why do we say that inductors consume reactive power, and so on and so forth? Why reactive power? So these are all construction of the human mind. They're all artifacts of what our elders decided to do. And again, it might have happened organically. These, again, the example of the Y3 phase, there's no real hard evidence anywhere, but what, for example, the IEEE Research, History Center have done, they have some you can look for them on YouTube. Old engineers are talking about their thought. They actually are thinking about what their elders did when they started from scratch. So, and maybe again, this our good old friend Nikola Tesla might have decided it for us. But at the end of the day, we are living with the decisions from the past. And now, if we are to relax some of these assumptions, maybe we can get something way different. I'm not going to argue. I think 3 phases here to stay. I'm not going to say we need to go 6 phase out today, but we might want to relax the assumptions and sort of get out of our old habits. And lastly, and I think this is really the one where kind of the second one is more from an intellectual curiosity point of view. The second one is actually more interesting for industry, is the fact that we want, just like, for example, you have all these documents. I know your colleagues at MIT are very good with that, Maria, creating pathways for decarbonization, for example, for different regions. And well, what if we could do that for network evolution? And really the idea here is, if we were to start from scratch today, or as of today, and look at the delta between what we have now and what could be. And considering how, for example, the generation mix might be evolving over the next 10, 20, 50, 30 years, well, we might also be able to give instructions, or at least boundaries of where networks should be evolving, or at least how they should be sort of following this evolution. So really, this is number one from a benchmarking perspective. So I want to look at, if I was to rebuild from scratch, here's the difference between what I got now on paper and what is currently in place, and see what kind, for example, what would be the economic gains, what would be the improvement in decarbonization performance, et cetera, et cetera. So really, that's one of the examples we wanted to develop. For example, I know we're going to get, fingers crossed, there's one of our labs, associated labs with the Natural Resources Canada, which is the equivalent of the US DOE. They're really interested in having case studies of, for example, metropolitan areas. So if, for example, and I'll give you an example from here in Canada, the Greater Toronto area is one of the most expensive place to buy real estate. So if the utility, for example, if they want to increase the circuit capacity and they need to increase the size of their right of way, it's almost impossible to do it, because the acquisition cost of the land is so high that they have to look at other solutions. So the idea here is that, what if we were to restart from scratch, reboot for this area, and to sort of see what could be a different solution, and kind of guide the planners on how perhaps they could diverge from their current course into something that might be better. Or at the end of the day, we might get the answer that, well, what you're doing has been doing pretty well. There's not that much difference between what you've got there and what sort of the ideal, or what the academics think is ideal it is. So, and that would perhaps give them reassurance that they've been doing their jobs right. So that's really why we want to do this. Bye, Alberto. Nice to see you. So then the other thing we want to kind of look at, what should we try to achieve? And this is where, again, it's going to go. I'm sure no one here will be in full agreement with what I'm going to say, and that's the whole point here, and that's the point of getting this discussion started. And it's very much a philosophical question that we need to ask, and that's why it's exciting research. So the first thing I'm going to say is that, what are going to be sort of my guiding principles in attempting this? And this is where each person and each group can come with their own biases. Again, if, for example, a utility was to do that, well, they could come with with basically their guiding principles from the corporate level and how they would translate that in planning objectives. That would be a different story. So my first guiding principle will be, I'm still looking for efficient resource allocation, which kind of, I would say is a bottom line here. Though by efficient resource allocation, hopefully, and again, that might not be happening right this second, I want to include things like obviously labor, capital, and materials, including life cycle impact. I love batteries. I think they're great, but they might have, again, a little blind spot in terms of their life cycle. Do we need to go mine some rare materials in war-torn countries in Africa? I always want to sort of see this, the global picture of how resources are allocated, really take into account all the externalities that might occur, that might come by. The other thing, so my second principle is that anything that we do in terms of network evolution should lead us towards 100% or very close to 100% carbon free or very low carbon. So that's kind of also something that I'm looking for. Resiliency, and I'll talk a bit more about resiliency next. And then the last one I want to say is that I think whatever networks we're building should be seen as a highway system. When you could have tolls, but the toll road should be that no one should be denied access. Okay, so the non-discriminatory open access, there's this notion that the network is a public good that should be open to all who are capable of using it. So we have open access, we've had open access, correct me if I'm wrong, Maria, since 1996 in North America, roughly.
For the rate 88, yeah.
So officially, at least from FERC's point of view, it's been so 888, 889 since the middle of the 1990s. But while now we're sort of creeping into distribution networks, now we're at order 222.
Yes.
I'm missing a two.
Four twos.
2222.
Yeah.
So now the spirit of the 4 twos has to be maintained also in distribution.
So François, I'm sorry to interrupt, but this business about going all the way to materials and capital, I just strikes really the chord with me. Right now in Serbia, there are demonstrations against open and lithium mine. And you see that in a lot of, poorer countries where there are these resources. So look, your point about the entire life cycle, and you're not the only one pointing out, there are people like Bayat, Lester, Lay, they all pointed out that, when you decide what is an efficient resource allocation, you have to go and look at life cycle. It's not just fuel costs that we do in optimization on day-ahead market. So I just wanted to stress that point, that actually it has all sorts of social implications. It's not just, if you use this material or the other, or how much there is, it affects people's lives. Yeah.
Oh, absolutely. And again, here, when I'm talking about resources, land use is the same thing. So are you going to be burying? Are you passing? Where are you passing? And obviously, if we're taking an engineer's view, it's just a graph, right?
Right.
But the graph passes somewhere and it uses land resource. So it's also part of the resource allocation problem here.
Thank you.
Okay. Thanks for the point. So if I'm looking from now, what are the design variables? And this is, again, I don't think it's it's not an exhaustive list. And I'm obviously putting my engineer's hat on and I think the ordering of these actually could change depending on your priorities. But obviously, available technologies have to be part of the deal, including batteries. So wire and non-wire alternatives have to be treated on the same at the same level. But this is where my bias is. I think wires are quite effective and are quite simple in terms of, obviously the maturity level is we can't even discuss. There's no discussion. So wires have been dangling up in the air for many, many years, and they're going to be dangling in the air for many, many more years to come. So obviously, but I think we need to be open-minded and be willing to look at these new disruptive technologies. I know there's these now these technologies that can tune the impedance of a line to act a little bit like a phase shifting transformer. All these things, again, should be looked into. And again, maybe not as a grand theory of everything, but we need to look at case studies, and we need to look at how these things might be able to hinge in the market. Really, so the second point, really from the perspective of really the problems, I want my students to start doing some number crunching. Obviously, the network topology is the next in line. So connectivity, sizing of links, whether it's switchable or not. These are, I think this is the bulk of where the work is going to happen. We're taking into account, the guidelines from before, and how these will actually, the guiding principles, excuse me, that will sort of get all of this together. Control approaches, I'm sort of, again, not so sure as to where they're going to come in, but there's always the best example. Let's say if we're going to more and more inverter-based resources, I have this philosophical question I typically throw at my students. What if you have an isolated power system where all resources are inverter-based? What's the meaning of frequency?
So we have Sairaj Doppel on the Zoom. I think he's still on, and he can tell us that our U.S. Department of Energy awarded the entire large consortium project to be led by not NREL, National Renewable Energy Lab, but Minnesota and other schools are members of that consortium. And this question has to be put on the table. I agree 100%. And it sort of comes in that work. Sairaj, are you there? I don't know. Yeah, you are there. So maybe you want to say a little bit more if that was addressed actually at all in your proposal. What is the frequency if you have all inverter things?
Yeah, this is highly philosophical, very enjoyable comments here, François. Again, we don't want to be disruptive at that scale, right? Where if you say all inverter frequency is meaningless, let's completely, disregard it. That really raises a lot of eyebrows. We tried to say we're going to keep as much of the control architecture going up to the tertiary level intact, so that people are not bothered by disruptions that are happening on the physical infrastructure. And that's sort of where we tried to draw the boundary.
Yeah, I think that just an old timers take at this, the same way in the bulk power systems, you have to have a slack bus, which really determines the time. It used to be, time error correction. If you go all the way back to that, frequency was very important. I think probably a sort of off the top of my head answer is that you are going to have at least one source that's going to create.
Well, you always need an anchor. You'll need an anchor that is a surrogate for the integral of the power balance over time.
Right.
But this is Daniel Herring at Lincoln Laboratory. I'll just jump in and say, again, AC and DC are legacy analog constructs. If you look at what signal waveforms are used for radio and Ethernet and other digital age technologies, you have engineers looking at, I need to push information. What's my most efficient information encoding rate, or my most efficient utilization on a cellular area? There's different ways of looking at current and voltage from more an information theory or other point of view, that if you're not constrained to be compatible with an incandescent light bulb or a spinning synchronous motor. There may be better waveforms to use. Over.
Yeah, there is a lot of soul searching in the group that Daniel is, and I'm, I work there too, is on the, how do you make all these parallel inverters work well, even in some tactical microgrids, you're out in the bases, air bases, and so forth. That's the type of work that's going on. And all I can say, there are a lot of open questions for research for community. That's
yeah, no, definitely. So again, frequency. What's the meaning of frequency? And going back perhaps to the control approaches, I've been, you might. I had a PhD student was co-supervised with my colleague Geza Yosh recently, and we had a I had a fundamental disagreement with him that he wanted inverters to behave just like synchronous machines. So there's a lot of research on virtual synchronous machines, which I think, let's get rid of that old piece of junk, that has all these complicated dynamics where we can have, a P and a Q reference within microseconds. I want this. And so, my name is on the paper. I might not agree fully with it, but the bottom line here, there's a lot of questions on that.
Q has no meaning at a microsecond
True.
level.
True enough.
And so, when you start pulling on
Daniel,
that
let's postpone it for after François finishes, but Q dots does have a meaning, and we've had infinite discussions on that. So, François, why don't you charge ahead? Sorry, Daniel, we have like 10 more minutes to finish, and then we can have discussion. Okay. If you can.
All right, so I'll speed it up then.
No,
not to speed it up too much.
We're enjoying your discussion.
Good. Well, there's questions, and it was meant to stir the pot.
Yeah.
So obviously market structures. So now you've got, New York Rev wants to go with the LNP markets all the way down to I don't know if I've not. It's too bad Alberto is gone. But what's the plan with New York Rev going with DSO markets? Are you going with LNP all the way to the last socket in your home?
There is no plan, just the realities, and going back, sort of to your overall assessment, high level assessment. New York only has 11 zones or as many zones for load. It's nothing even close to local.
No, but I know you're working, and NYU has been working on that sort of the coordination between ISO and DSO markets. So there's this notion that yes, the LNP at the end of the day, if you go all the way down to your last socket, 120 volt socket in your home, while it's a linear superposition of your zonal price with loss components and so on and so forth all the way down. But so the market structures, I think, might be design variables. I know my student Abdelrahman, this is what he's looking into, how actually sort of the market structures, how the transmission and the distribution speak to each other will influence what kind of outcome you're going to get. And also at the end of the day, if we're going to go over larger areas, there's a need for a different model of governance. Right now we have the governing councils, the coordinating councils like the NPCC, like New England ISO, Ontario, Quebec, and Atlantic Canada are a member of. But I think NPCC is directly connected to other two giants, through MISO and PJM. And so when I speak to traders here in Quebec who see transactions from Hydro-Quebec traders into SPP, well, these things are happening, and we need to sort of look beyond our nose here.
So at the expense of interrupting too much, I just want to make one point before we lose your slide. It is the previous slide. I think it's what we are finding out. If you just look for control by itself in outside of context of these other design variables, you do much worse. So we are doing a lot of work on what one can think about control code design. There is a trade-off between the hardware and available hardware technology and designing, bringing control from the beginning. And it's known as the technical term as control co-design. I think we can do much better in terms of designing these systems if you look at their interdependencies of these variables that you have. Just the point that if we study them standalone in silos, it's just we are not going anywhere again.
And I think my last point, and it's not in the slides yet. As I said, this is a work in progress. I'll talk a little bit about that before I conclude. Okay, so resiliency for me this is where I'm getting bombarded all the time. Folks from the Auditor General of Quebec have come to me to out them on a mandate they have, and the word resiliency comes all over the place. But right now and I've asked Jalen, my other student, to just do a survey of the definitions out there, and no one seems to agree on what it is. I think I kind of like the DOE's version, but that being said, it varies quite a bit. So some, and there's no real quantification. The only thing we've found so far, so there's work by Matteos Panteri, who was at the University of Manchester at the time, with Pierluigi Mancarella. And I think they were working also with Nikos Atsergeriou from Technical University of Athens. So they came with a number of metrics, but they've also talked about this trapezoid of resiliency. And I think this is the next step really will be to take in this notion of having a certain level of resiliency. It's being degraded through some event, and the time it takes for the trapezoid to be restored, a bit like what we used to, when we had go back to the Iliaco papers from the 1960s, 70s, with the different states. Well, I guess we need to develop a similar sort of state approach to look at how resiliency sort of evolves over time. But my question is, if we are going to be designing networks from scratch, how do you integrate resiliency as part of the design process? Right. And so this is where I'm really struggling with that. So that's one of the first questions as part of our agenda. It's how to integrate these targets, and perhaps what are the targets themselves. This is something we're still unsure. So one example would be if, let's say, you have a basket of bad things that can happen: hurricanes, solar storms, cyber attack, I don't know, and whatnot. Well, we probably want on a design at the design level, we probably want to minimize the area of the trapezoids associated with these quote unquote deterministic events. The thing I like most, because I'm a stochastic person, is to perhaps put a chance constraint or chance constraints on having that the probability of the basket of metrics are not met. So that's also one thing we want to look into, or just basically put boundaries where we want the design to sort of lay, and to kind of see how the network solutions would be affected by any of those measures to sort of build in resiliency as part of the design problem. The other thing is also that I kind of, what does a resilient network look like? If you want to build one, might as well know what one looks like. And so this kind of brought me back to there was an old paper by Salmeron and Baldic from the sort of middle of the 2000s, obviously sort of post 9/11 in the US, where there was a lot of investment in terrorist threat assessment. And obviously, for example, if you look at how the Colombian guerrilla warfare were attacking the electricity grid on a almost daily basis. So one thing what we want to try to do is to look at these terrorist threat problems where you're trying to find the most vulnerable points in your network, which basically should be the ones that will threaten your network or will actually cause the most damage. And we'd like to do this on a very large number of samples of networks. If we can find samples, that's the problem, and kind of mine out of these what are the features of very resilient networks, so where the terrorist would have to put a lot of effort to bring it down, versus one that is where there's very little effort, the terrorists, again, here the terrorist could be a storm, could be a cyber attack, could be all sorts of different things, to take your network down. And obviously here the focus is more on the physical infrastructure, not the cyber yet, and I don't want to go there. But really, what are the features? What, if I'm looking at a database of networks, transmission, distribution, what kind of thing that I should be looking for to replicate in my next generation designs? If I were to start from scratch, what kind of feature I want to hard code in my design? So obviously this is data driven. Considering how data is not available for this kind of information, we'll revert to synthetic networks. It's obviously the EU Pegasus work that's generated a lot of traction, at least on the transmission side, or at least a large transmission side. And then there's Tom Overby in Texas that's done quite a lot of work also for more North American flavored networks, all the way down to distribution. There's also, I had a master's student who did this for Hydro-Quebec networks because they were interested in doing hosting capacity studies on typical networks. So that's also something we can sort of piggyback on. Now, this brings me to sort of the kind of the last, which is the last slide of my presentation, but I have more stuff to say after that. The new generation landscape is really, again, if you want to get, for example, people excited about this, I think this is really where people will want to jump in. So now that we've got a lot of rooftop PV, small batteries behind the meter, how really the question is, what do you need for a DSO to really become an SO, not just a network operator or network owner? Well, when I'm looking at how feeders are, or how the distribution part of Hydro-Quebec is structured here, at least from an electrical perspective, well, if I want to ship meg or kilowatts from a given feeder to another feeder in a different area of the province, well, I have to go through the transmission system. So the transmission system is the glue of all these little feeders because they're all radio at the end and they don't connect with each other or very little. So the transmission, to make that possible, well, the only way for that to happen is for the transmission system to either move up higher in voltage. So for example, if I'm comparing in the UK, anything below 132 kV is distribution, whereas here where I am, anything below 25 kV is distribution. So the sub-transmission level is not part of the picture. So that's really what. Oops, sorry. So this is really one question. So really, if we want this to happen, well, the DSO, the system operators at the distribution level, well, they want their transmission system to just look like a copper plate. So that's because they want to be able to interconnect their customers or their DERs to maximize their welfare, to basically provide this open access. On the other end, when I'm looking at the transmission system, and typically if I'm being a bit dramatic, well, I don't want to say dramatic here, transmission system operators, they want to have an easy life. Their best scenario is that the demand minus whatever generation is flat throughout the day. They have one dispatch set point and everything is a-okay. So how can then the question is, how can we get the networks to approach this as much as possible, where the DSO can really become a system operator to enable matching of supply and demand, while at the same time the TSO can get its bang for its buck by also making it easier to flatten its basically generation load balance over the course of the day. So that's really the thing that I want to sort of discuss here. At least we want to, and this is something that Abdelrahman will be working harder on. And then finally, I guess I'll just start to I'll finish. I'm running out of slides. I'm really sorry about that. The large scale renewables is the last frontier here. And obviously, in the case of when the Quebec government in the 1960s, 1970s decided to go way up north and not go nuclear, go fully hydro, obviously there was a humongous environmental cost. There was an enormous capital costs. Aboriginal communities were disrupted, were moved around. There's a lot of land that was flooded. So that, if we were to start from scratch today here, that wouldn't fly. That wouldn't probably fly anywhere in the world. It's done, we'll have to live with it, but it's coming to a place near you. And I think this is what at least citizens or residents of the United States will have to get used to. If we want to really decarbonize, we're going to need more transmission. And this is where there is, once we sort of understand how on a more local scale, DSO and TSOs should sort of look like, well, there's the next, just like the networks of microgrids, so network microgrids or interconnected microgrids, well, we need to sort of go and how we can sort of go beyond, go bigger. And really, I'll just steal one of Mark O'Malley's running gag here, where he's basically using he's also stealing President Eisenhower's words. Was when he basically proposed the interstate highway system. Well, let's make the problem bigger, and this is where we're going to be able to fix this, to make it happen, is by making the problem bigger, by again leveraging the fact that we've got people who are under the sun, people who are not, and this is really where I think the UI, at least, and this is very editorial statement here, the United States has to build the highway system for the 21st century, and actually it is in terms of aluminum in the air.
Thank you very much, Francois. This is a lot of thinking, to rethinking, a very thought-provoking presentation. I think that since we do this just 1 hour, 11 to 12, people who want to quit, they can quit, but we can continue another half hour if you guys want. So let me go and call some people to state their questions now. So Daniel, I think you have the first question. You want to just state it yourself?
Well, yeah, so, the electrical network is still the largest physical machine in existence, but information technologies, information networks are now the most complex machines in existence. I was wondering, what inspiration do you think we can or should be taking from those other networks?
Yeah, I've always struggled with that, and again, this might be because this is my personal bias. I'm a power guy. And in power, we can't afford losing packets. And in power, if the packet arrives after the other one, and if they're out of sync, we can still descramble them, and they're buffers. Perhaps it comes down to storage. If we're capable of offering sort of this, the buffering that is entailed in digital communication networks, perhaps that might be possible. But I think I need to have a more serious discussion with colleagues whose sort of training is in digital communication first and foremost.
Can I throw one more wrench, Daniel, to your question? I think that really depending on how you model the power network, what assumptions you make, we have this problem of what's known as counterflows in power systems. And if you just think about power network just as transferring flows, real power flows, not having oscillations back and forth with Q, then that problem, assuming lossless things, that problem goes away.
I'm just, if you're putting everything on the table.
So sure,
where you can change the waveform.
Networks cannot handle counterflows.
Well, but there's oscillations in the internet also.
I
there's-
think there are some lessons to learn. When I was at NSF many years ago in late 90s, serving there as program director, there was another program director from social economics department there, and Sam Jelinek, and she and I spent a lot of time over coffee talking about the analogies between airline industry and power industry, how the type of changes that François was talking about, you go from very large scale to a lot of distributed to smaller airports rather than centralized airports. And so there are those analogies. I think probably I am sort of with François that when it comes to it is a good question. And once long ago, if you look through my CV, I did write that when I don't know where I was at Illinois, I did write about those analogies with information networks and power networks. So we can continue the discussion. But
yeah. No,
I might add that
there's some different market opportunities and ownership models and what have you. And Ethernet was perhaps the dumbest network technology of its time, but it succeeded because it put the smarts in the nodes, not in the network switches. And just, there's things like that where there's just a lot of people explored growth of complex systems and the market dynamics and other things, and they ended up with a very different optimal point than where the power industry is starting.
It's worthwhile exploring further. Let's leave it there. So thank you.
The other thing the one thing that I guess, telecommunication networks are subject to KCL. KVL is a real.
That's exactly that one, which deals with what, that is really what uniquely differentiates it. Let's follow up. I will make sure, François, that we connect with Daniel and follow up. Maybe there is a paper.
Absolutely.
Here. Okay. I think I'll skip mine, but I just make a comment that I believe you were talking, François, all the time as that, and my friends at MIT who do decarbonization paths from Hydro-Quebec to Massachusetts, for example, work under the assumption that today's transmission cannot transfer more than it's transferring. Okay, so this is a real misnomer because we are operating, in the preventive way. There are a lot of reserves. This is a very interesting anecdote. When the restructuring started in electricity, that was back to Galiana and Schweppi, I think whoever was the CEO of FERC at the time said, okay, we have more supply than demand, therefore there can be competition in supply. That's what started it, because demand was forecasted to be higher. And then somebody asked, do we have enough transmission to deliver this under competition? And even one of my former students who had a startup at the time did a study to say, oh, we have 30%. On the average, 30% of the transmission capacity is used out of 100% thermal capacity. I think that was real disservice because FERC said there will never be congestion problems and stuff like that. And so I think the truth is somewhere in between. And this is where the control and flexible utilization of reserves and resources, and maybe even smarts that Daniel is talking about in the nodes, adjusting so that you don't create congestion, so it's all interactive. That's where I think there is a lot of room to make more out of what's available. And so I would actually, I'm not 100% sure if you assumed that like there is not enough transmission and we have to automatically build more, or can you comment on that a little bit?
So the one thing, hold on, let me just see if I can stop sharing. Okay, so obviously the assumption is that we are starting from scratch. So yes, after that we could look at what's the difference between what we have now and what might be. And that might give us some intuition about how much extra capacity, because that's and I've had some heated discussions with colleagues also colleagues, is currently, if you're looking at the business model of interconnection between Quebec and the United States, anywhere, be it Massachusetts or be it New York, it's firm delivery of energy and of story, because it provides a fixed income and it's risk-free essentially. So if you have to put a ban on top of it, so headroom or footroom for doing flexibility, there has to be a way to monetize the use of the flexibility, and I guess the markets are still deficient in that respect.
Absolutely, and yesterday and day before yesterday, we had our Alberto was there, the program on which called Perform. There is academic set of projects that we are working with Lehigh on how do you actually, make the case for flexibility. But it was in context more of how you manage uncertainties, but it's pretty much the same question. So don't let me take too much time on this one. I will follow up on this because I think it's important. I know that you are managing a lot of IEEE planning things there. And so I think that this question should be really addressed, but I'll follow up with you now. Let's go to Rabab. Rabab, you want to state your question?
Sure. Thank you so much for the presentation and all of your thoughts. I guess I come wearing my Canadian hat today as well. And so when you mentioned the guiding principles, two of them really stuck out to me. That was 100% carbon free and the non-discriminatory access. And when we're looking at the Canadian context, in northern communities, which right now don't have any kind of electrical grid system and they're not interconnected, really are kind of this great way to build for a specific test case and build new because there's nothing there. But I was wondering if you are planning to look at that as part of your research, and if you have any kind of initial thoughts on what that system requires and what we can do.
Yeah, this is a very good question. I will say, we've in my group we've done quite a bit. We've had some grants on sort of northern communities developing some approaches as to whether or not networking them makes sense. This is a very it's a tough question, because if, let's say, I'm going to take the example of Australia, and this is always where it blows my mind when there's a 400-kilometer long distribution feeder to feed a very remote location. Now, if I'm looking, for example, in Quebec, there's 23 off-grid communities. Some of them obviously are not. Some of them, for example, there's Magdalen Islands, which is a small archipelago in the Gulf of St. Lawrence. So Hydro-Quebec has basically decided to close volley. They're going to keep the diesel power plant on the island, but they're going to build an interconnector to the mainland with the goal of obviously decarbonizing generation there, and also increasing resiliency, because every time there's a big storm, very often they're having issues with supply. So that's one thing. When we're going way up north, it's getting a bit more complicated, and I guess this is where the economics need to look. We need to look into the economics really, and I'd like to know by how much they would gain if they were capable of interconnecting. And maybe at the end of the day, what they should be just doing is to connect to the south, to the rest of the Quebec grid. But if you're going even further up north in Northwest Territories or in Nunavut, it's getting a bit more complicated. I will say, I don't know. And there's also the issue of being exposed to pretty harsh elements, so that they still would require to have a backup no matter what.
Thank you very much. I think Rabab should have introduced herself. She's actually from Canada doing PhD with Anuradha Swami here at MIT. So that's why the question about Northern, I presume, right?
Yes, absolutely. It's something that I think about a lot, and I hope to eventually be able to work in that space as well.
That's great. Maybe you can connect with François later. So we have Masoud Barati from University of Pittsburgh. Masoud, you want to ask your question?
Yeah, but thank you so much for the presentation. I asked about the task function optimization. But my question is that So I think in order to deal with the rare events and also the resiliency calculations, we should at some point we should change the current calculation. For example, the chance constraint optimization, and also the scenario generation for the stochastic optimization problem. So for the rare event, we should apply the different calculation tools for that. So my question about how do you deal with the chance constraint optimizations? Because the alpha, which is the failure risk threshold value of the rare event, is very, very small value. So how do you, but if we want to calculate the probability of the, for example, the exitness of the system metric triggering failure for the specific constraint of the system less than the alpha, which is the very, very small value. So it's very hard to change this constraint from the probabilistic format to the deterministic format. So just
I will say this is something, we're so much at the beginning that I wouldn't be able to really give you a right answer, but I appreciate your comment in the sense that, well, number one, we'll need to try to characterize probability distributions, which I'm not a fan of. Number two, if you're, I understand that it's going to be, you might get into a situation where it's very sensitive to the alpha. That might, I'm expecting to get kind of all or nothing type solutions depending on the value of the chance constraint. I think stochastic optimization is probably easier to handle, but I'm still because it's very easy to translate it into a deterministic equivalent. So this is where I'm still unsure. I'll be honest. I'll be dead honest with you.
So I want to throw again the wrench into these top-down centralized planning methods. They actually really don't take into consideration at all the stochasticity and preferences and on the grid users. So as you know, François, we've been trying to push this diamonds framework, in which even at the planning stage, there was a PhD student at CMU, Maria Pritza, 10 years ago, who actually proposed this interactive planning using diamonds. You have to, and I think California ISO went a little bit into that direction. You need to get some information, bottom-up information from the end users about their needs for the grid, and then sort of have less complicated planning methods. I think probably at the end of the day, there are good ways of reconciling, the needs, end-to-end needs, because there is too much in everything that we were talking about today. There is too much pushing more than pulling for technologies. So at the end of the day, we are doing this for end users. And what is missing with today's markets, and we do a lot of discussion on that, you just have day-ahead market, which is very short-term, right? Everything else is not transparent. And how do you do this? How do you exchange the information longer term for planning purposes or for operational purposes, operational planning purposes, so that some of those preferences and even uncertainties, they get taken into consideration? Just the simplest thing. The states don't want to commit themselves to provide an information of how much load they're going to need for next 5 years. Okay, what are you building for? You put that question on the table, and there is really, it just destroys everything that we are talking about. How could you plan for something, let's say technologies at least 5 years, or longer, maybe longer, without having that information? So I am pretty biased now, talking about biases about the need for information exchange in the interactive way. Doesn't have, and when you talk to ISOs, for example, they say, well, we do planning, but we are only responsible for reliability day ahead and stuff like that. So it is really not on their map. And I think people like Frank Volak at Stanford, he advises Calais a lot. He's beginning to recognize that you really need longer term energy markets, for planning. So going back, Masood, to your question, the long comment is that we can no longer do this planning assuming that customers are willing to take that much risk, if there is no power or there's no delivered power. It has to be some interactive protocol, even at the planning stage, through the markets or whatever the governance is. So I'm just curious if that makes sense, François, to you guys.
Thank you so much.
And how does it come into everything? Because grids are important.
I just like to interject though that there may be ways of changing the system design so that less planning is required. That you have more general purpose infrastructure that can be reconfigured rapidly as needs change, and or you have less of a strong dichotomy between the owner of the production and the owner of the consumption, that there's a smoother gradient where people can meet custom needs on their own instead of being beholden to convincing another party to take care of them.
Yeah, but that goes back to the beginning of François' presentation, saying, can every solar rooftop plan for itself?
He was pointing that if every house is an independent island, that's inefficient because you don't have the networking benefits. But having a central planning coordinate, the central planning monopoly is the polar opposite. There's probably a happy in between.
And so this is why we were proposing this interactive in between. But at one point, you also were asking, François, what should be the function of DSO? I think that research, a lot of, sort of academic research, including what Rabab's team and Anuradha are doing, they're pointing out that for operations, and Lena at Harvard, that you can actually do a lot of operations in a completely distributed way and be near optimal. I think.
I agree. I totally agree with you.
Where system operator comes in is at this planning stage that I'm talking about.
No, but what I'm, there's kind of a dichotomy where we expect the, my solar on my roof to flow to your battery at the other end of the city. But for electrically speaking, there's no link. You have to actually pass through the transmission system for that to happen. So this is where, in some sense, we want to remove the shackles of the network. But if we want to plan properly, we can't expect the network to be a copper plate. So it's, the ideal, going back to you've got the two extremes, you've got the islands and the monopoly, but in terms of network structure, maybe the network, and as Daniel was saying, if it's reconfigured, if it can be reconfigured on the fly, if it's got a lot more alternatives to be, again, implemented in real time, while you might be able to get closer to our copper plate. Again, it's a reconfigurable copper plate. Maybe we can, going back to the telecom image, I can see the operators making the connection in the telephone systems, connecting the lines together. It's almost as if we should be going towards that. But you're very well taken about having the dialogue, and this is where I guess colleagues in the social sciences can really bring in an input to that.
This is a disturbing comment because it's not really just social sciences.
As
engineers, we should figure out that for planning, we should have interactive thing, because the answer is at the end, the social science, Econ 101 is going to answer. So you go that way, and actually there is no answer. I think you have to look, I believe, at these problems as really engineering problems and the long-term planning. I think Odon wanted to say something to this. I don't know. Odon spends all his time on decentralized planning. So
Hello,
What are you
François.
saying,
Good to
Gordon?
yeah, no, thank you, François. I actually missed out on most of your talk, so I.
Oh, that's fine.
But I like
No,
the
no worries.
discussion here.
Yeah.
So,
So we are going to have to wrap up soon. So
Yeah.
if you don't have a question,
I was just going to interject that, isn't there also one way of making consumers more engaged in this? One can do better contracts and maybe even moving away from this assumption that everyone has the same reliability. Start thinking about differentiating, or putting a price on who gets to receive so much electricity during times of scarcity, rather than kind of cutting off everyone or no one, depending on where you live, like what happened in Texas.
But there was a nice PhD thesis by Julie Karn, Visudeepan at not Visudeepan, Julie Karn, Siripa Julie Karn, who did PhD thesis in public policy at CMU. She really looked very carefully, and there are publications in IEEE Transaction Smart Grids, in which she said you really can talk about differentiated reliability beyond. And the big objection to that is, well, you don't want to make people unreliable. So you want to talk about some minimum social reliability.
Yeah.
And then
It has to be a very simple to understand reliability model. The ancient Romans with their aqueducts, they had a priority queue of water for sustenance, water for cooking, down to, watering the lawn was the lowest priority. And they didn't have to enforce it during times of plenty, but during times of drought, they'd put the centurion by the water spigots and make sure you weren't taking more buckets for excess purposes. If we had a similar thing where as the grid frequency sags, all of a sudden critical emergency lighting circuits stay powered, but entertainment systems trip offline. There are ways of having a social contract around shared differential reliability models.
But just to build on that, what Siripa did, this PhD thesis I'm talking about, I think it's really worthwhile looking in that work. She actually put the burden of proof on, and a lot of people, including Daniel, they're talking about microgrids just interconnecting themselves, not even going through transmission, right? And then there is this question that she tackled using machine learning at a time when people really were not using it that much, on if you are a utility provider on the distribution grid, when do you close and how many normally closed, normally open switches you need for reconfiguration in order to build economies of scale back through reconnecting the microgrids. I think it's a great work, and I think she published it, but it hasn't been connected much with utility. I should stop talking here. Zheng Zhu, I suggest we skip your question. We'll do that offline with Daniel, and just maybe close with Professor Yilu Liu's question. Yilu, are you still there? Okay. Yilu was asking, do we agree that there is a balance between transmission and storage?
I don't know if I understand the question. Is it because if we consider them on the same footing? I don't know. For me, storage is moving energy across time. Transmission is moving energy across space. So there's obviously, if you're this idea of having an east-west link is trying to do that by taking into advantage of time zones, but really if you're looking at the continental scale, when it's, let's say, midday in the Midwest, you've basically got the sun everywhere. The interest I think would be on the edges when the sun is moving into the continent and when it's moving away. Then you might get some interesting arbitrages there. And I know the folks at NREL have done quite a bit of work on that.
I think Yilu had to go somewhere, but maybe I'll follow up with her. I think it's 12:30. We can probably spend the afternoon still discussing among ourselves. So let's finish. Francois, thank you so much.
I think Auden wants to say something.
No, I
Let-
was just curious. Sorry, to extend the talk, but did
Go
you talk
ahead.
about markets? Did you have the solution
Yes,
for
yes,
markets,
Well,
François?
Well, this is in my mind, there's a question. I know my student Abdurrahman is looking into that, and the kind of level of involvement of, and the kind of relationship between the distribution and the transmission are sort of the key to evolve in my mind.
Makes sense.
what was the question? I don't know exactly.
No, I was just curious about François's message around markets and the role of markets and whether they
Right,
need
so
to
the
be
way I
fully.
took it as a listener, he had a list of principles and for design variables. And one of the design variables was, build life cycle, analysis of materials and so forth. But there is a variable which is market structure. And there is, right, that's what you were talking about.
And it was Maria. What I'll do, I'll wrap up because I had a couple other points. One thing that I want to mention, and then you can close the link, is one of the challenges in doing this kind of work is how do you represent real-time operations in planning problems?
Absolutely,
And
yes.
And this has been one thing that we've been able to do something.
Yes.
The low duration curve was the best invention since sliced bread. Now it doesn't work anymore. And looking at different ways to compress out the time dimension is the next frontier.
Yes.
That's my last
I agree
message.
100% with that. I actually have a startup that doesn't have a website, but basically one of the big toolboxes is looking into that. You can actually make it much more adaptive, but changing the rules so that at the planning stage, you take into consideration the effect of demand response and stuff like that.
Yeah.
There is no regulatory mechanism or financial mechanism, but actually you can do it technically. So I want to close just by saying that maybe this is very biased, but I've gone through more than 20 years now on our market restructuring, everything. It started with saying, oh, all these changes can be handled by Econ 101. Now we go to meetings like yesterday and basically said, implementing physics of markets, I forget all on what they say. Implementing physics in markets is hard, but it's even harder to implement markets into physics or something like that.
Yeah.
They said something like that, right? So I think what this is saying, it's really saying that hard to do for young people. We have a lot of young people, including Auden around and you, François, but it is what we need to nurture is how do you do these interdependencies? How do you build synergies? When you do planning as an engineer, you take into consideration the lifetime and the effect of operations and stuff like that. So it is up to you guys to actually push all of these. François, I don't know where you're going with these thoughts, but maybe you should write some survey paper or do the IEEE working group on this, I think.
Yeah, well, one thing we've done is we're doing planning not in the time domain, we're doing it in the state space domain. We're doing it in the face plane.
Really? No, I'm saying, where are you going with the entire subject of if I were to do it again, how would do it?
Oh,
it almost deserves, I think, IEEE working group.
Well, I guess, there's the under power system operation planning and economics. I guess I'm speaking from my church. There's a bulk power system planning subcommittee. I think it's Masoud Barvania from University of Utah, who's the chair of this one.
It doesn't ask questions that you were asking today. I'm sorry.
No. But you know what? This is it started as a pure academic research exercise. That is, at the end of the day, I'm not expecting utilities to come knocking on my door. However, as I said in one of my objectives, is to create benchmarks. And this is where the industry folks could come in and look at it.
Perfect. Okay. Thank you very much on that note. And thank you, everybody, guys.